Let's understand surface tension in this video.
Have you ever seen water form beads on a leaf? Or an insect walk on a pond? And wondered why?
Surface tension is the reason.
And it makes the liquid surface behave like a stretched elastic sheet.
In simple words,
Surface tension is the force along a line on the surface that tries to shrink the surface area.
we can also see surface tension as
The work needed to increase the surface area, that is, energy per area.
this happens because liquid molecules pull on each other.
A pull we call cohesion. So surface molecules feel a net inward pull.
Inside the liquid, forces cancel out.
But at the surface, molecules have fewer neighbors, so the surface acts like a tight skin.
Surface tension is written as T
Or sigma, and its SI unit is newtons per meter, while in CGS it is dyne per centimeter.
Mathematically, surface tension equals force divided by length.
T equals F divided by L, and it also equals work divided by area.
Now let us look at a short solved example to make this clear.
Question number 1 asks, find the surface tension when a dragging force of 12 newtons acts over a length of 4 meters. Use the formula T equals F divided by L, where F is the force and L is the length.
Plug in values.
T equals 12 newtons divided by 4 meters, which gives 3 newtons per meter.
So the surface tension in this example
Is 3 newtons per meter.
Surface tension comes from cohesion at the molecular level,
And it explains many everyday facts like droplets becoming nearly spherical.
small droplets form a sphere,
Because surface tension tries to minimize surface area and keep the molecules together.
surface tension can be measured by many methods.
For example, capillary rise, bubble pressure, spinning drop, Dunui ring, and stalagmometer methods.
Factors that affect surface tension include
Temperature, soluble impurities, and dust or oils on the surface.
raising temperature lowers surface tension.
And some soluble substances like common salt increase it, while soaps decrease it.
Surface energy is the work
Stored when a surface is created, and it equals surface tension times the change in surface area. ES equals T times delta A.
Now we move to capillarity.
The rise or fall of a liquid in a thin tube, which depends on surface tension and the contact angle with the tube material.
The angle of contact is the angle between the liquid surface and the solid surface measured inside the liquid, and this angle affects whether the liquid rises or falls.
For a wetting liquid like water on glass, the contact angle is small and the liquid rises. While for non-wetting liquids like mercury, it is larger and the liquid falls.
The capillary rise height is given by the ascent formula.
H equals 2 times T cosine theta divided by rho g r, where rho is density, g is gravity, r is tube radius.
Durin's law follows.
Since T, theta and g are constants, the height h is inversely proportional to the tube radius. So narrower tubes give higher rise.
Let us solve the longer example from the notes
To see these steps clearly,
Question number 2 asks,
a 5 centimeter long capillary tube has internal diameter 0.1 millimeter and is dipped in water with surface tension 75 dyne per centimeter. Find the rise and whether water will overflow. First, convert units. 75 dyne per centimeter equals 0.075 Newton per meter, and diameter 0.1 millimeter gives radius 5 times 10 to the minus 5 meters.
use H equals
2 times T cosine theta divided by rho gr, with cosine theta equal to 1 for complete wetting, rho 1000 kilograms per cubic meter, and g 9.8 meters per second squared.
the numerator 2 times T
is 2 times 0.075 equals 0.15. The denominator rho gr is 1000 times 9.8 times 5 times 10 to the minus 5, which equals about 0.49. So H equals 0.15 divided by 0.49 equals about 0.306 meters.
This is about 30.6 centimeters, which is much larger than the tube length 5 centimeters. So water will rise to the upper end. It will not just rise halfway, and it will not overflow out of the tube. So what do we learn from this? Surface tension is a force and an energy effect caused by molecular cohesion. It sets droplet shapes, drives capillary rise, and shows up in daily tools and nature. Let us quickly remember. T equals F divided by L. Surface energy equals T times change in area, and capillary rise H equals 2T cosine theta divided by rho g r. Keep exploring examples, try the measurements and unit conversions yourself, and see surface tension in soaps, wet towels, and plant capillaries. Thank you for learning this with me. Stay curious and keep studying gently on EduRev for more clear explanations and practice.